My name's Peter Blanken. I'm a professor at the University of Colorado, and I teach and research classes in water and carbon cycling and climatology and hydrology. What inspired me to write this textbook? I'd say there's a couple reasons. First off, water is so important to our lives and to the planet. It was kind of this feeling that it would be nice if I could put everything I know and everything I think is important about this subject, if I could put it in one place. So kind of collecting my thoughts and summarizing what are the issues right now, what are the topics that I think are important. And and I came to that conclusion, what are the topics that are important, just through my work and my research in the area. Um, I think water is sometimes the underrepresented molecule. I mean, of course, like carbon dioxide and other gases and compounds play a very important role, but we need water to live, so it's pretty important. So I was writing, that was one of the main reasons. The other reason is that, well, a couple more. One is I wanted to make this subject accessible to a lot of people. And there are a lot of great textbooks out there, those that are dealing with the meteorological aspects of the water cycle and those that are dealing more with the engineering or policy aspects of water and hydrology. But I couldn't find one that did what I tried to do in this book, which is to represent the basics of what is the water molecule and does it play such an important role in the climate system and in our lives and shaping our lives and the planet. And also not assuming that everybody has to have a background in the natural sciences or some other subject area that would preclude them from an interest in understanding more about the topic. So I wanted to touch upon that too, and to make sure that that those that think water is important, and I think all of us do, that there shouldn't be a phobia that, oh my gosh, there's chemistry or math involved, and there is, but that shouldn't be a barrier. And then kind of the third reason is just what my students have taught me, what they think is important and what they're interested in, and I tried to reflect those topics in the book also. It was one specific class that I took as an undergraduate. So I can remember the moment that I got interested in this. It was a field class that I took as a upper division undergraduate student. And up until that stage, I'd been, of course, taking a lot of classes and sitting in a lot of large lecture halls and looking through a lot of textbooks and those kind of things. And I took a field class where we went up to the high subarctic in Canada and spent it was 2 or 3 weeks, I can't remember what it was, in the field, actually taking measurements and looking at aspects of the water cycle. And not talking about it in the classroom, but actually taking measurements. And I got really excited about that because I thought, oh my gosh, we can be outdoors, playing with instrumentation and taking some measurements. And I thought this is really interesting, and it's not all about just looking at computer screens. So that really sparked my interest, and I thought, wow, this is people get to work outside and to measure these things and have a career doing so. So I've never looked back, and I've still been interested in the water cycle and for forests and lakes and wetlands, and it started with that one particular professor in that one particular class. One of the ways I can find I can really connect with the students is if I reflect on my personal experiences. And so just 15 minutes ago in my class, I was telling them about some upcoming field work that I have coming up. And I always tell them what I'm doing, and I always share the recent analysis and data and pictures of where I'm going and what I've seen and what I'm doing. So I'm trying to give them that feeling that yes, professors do things outside of the classroom, and we have a life beyond those walls. And so I can't take them out into the field. Some of them I do, but with a lot of students, I at least try to do that. So So I try to share those experiences with them, and I try to do that in the book also to the extent that I can. So I've tried to include, pictures and photographs and the instruments that I've used over the years and the unique places that I've been that I've never would have gotten to go to if it wasn't for research. And I share that with them, and that really sparks their interests. So I do that. And the other thing I try to do is give them many examples of things that we have to calculate and we have to understand. I work through calculations with them in the classroom on the blackboard. I still use the blackboard sometime, and I force them to come up to the blackboard and to write out equations, and that's the way that I learn also. So I've tried to also put that in the book, work through examples, so they can model their responses after ones I've given them in the book. So I vision that the book is really in three parts. So there's the first part is the kind of the like you were mentioning, the introductory to the importance of water through a historical perspective, all the way back to antiquity and looking at the Greek gods and the Roman bathhouses, and just to give some sense of how important water has always been throughout humanity. It isn't a new issue. It's always been an issue. So I start with that, and then we jump into ripping the molecule apart. And so my philosophy is that if I just jumped in and explained why water is such an important molecule in terms of its density or chemical properties, that wouldn't get us very far. So my approach is that I go over the basics of the molecule in terms of looking at the properties and discovery of hydrogen, and the same for oxygen, and then review how they bond together in terms of the covalent bonding. And in that part of the book, again, assuming that no prerequisites and no initial understanding, if you understand these basic principles, then you'll understand everything about the water molecule. So that's the first part. And my feeling is if some students will, that could be their first exposure to those topics, and for some, they know it cold. So if they know it cold, and sometimes when students think they know it cold, often they don't, you could just pick and choose the chapters that you say, oh, I'm good with that. I can just go on to the next part of the book. So that's the introductory section, or the introductory few chapters. And then the second part of the book, I'd call that the abiotic environment. So that is looking at how water has shaped the planet around us in terms of landforms, and looking at cold regions, and how those properties of the water molecule that were covered in the first section, how those have played a role in shaping the planet that we're living on. So again, landforms in warm and cold regions, phase changes, evaporation, precipitation, all of those concepts and principles and examples are dealt with in the middle part of the book. And then the last part of the book, I'd call that the how water shapes the biological environment. So that's how water has influenced and shaped and plays a role in not just vegetation that I see outside my window here, but the vegetation, people, how water plays a role in aspects of water in humans, which is rarely covered in books, and insects, endotherms, ectotherms. So how water has shaped the biological environment. So kind of the introductory to the concept of water and the understanding the molecule and its properties, how those have shaped the abiotic environment, the non-living environment, and then in turn how then we move over to the biological environment. And then at the end, we do a little bit about climate change and also water quality in terms of I focused on microplastics in that part of the environment, but things like harmful algae blooms, and those are covered too. One approach that I take is I do not present equations and concepts without explanation. So some of the really good hydrology books will just present equations without any explanation as to the process behind where that equation came from. And so here's an equation and just trust me and use it. And that's always bothered me. I always want to know, well, where did that equation come from and why are we using it and what are the principles behind it? So I've divorced myself from that approach completely. So I always try to explain where the equations are coming from and why they're so useful. So an example is like Ohm's law. So I'll explain the concept of in terms of um, circuitry and the basics of that fundamental concept in the equation. Then I'll apply it to different things, as opposed to just jumping in with the equations and not explaining why we're using the concept of resistances and conductances to explain how much water a person needs to drink to stay hydrated. So I do that. And the other major thing is this the holistic treatment of water. So it's not just surface hydrology, it's not just groundwater hydrology. It's a lot of everything. So it's the role of water not just in shaping the landscape, but it's also the role of water in humans and insects. And those things are not covered in hydrology books, traditional textbooks. So I've gone instead of taking a narrow path and diving into it very deeply, and there is a need for that also. But I've taken to approach. I've tried to give the kind of a spectrum of the importance of water um, on our planet for not only the landscape but for those that are living upon it. Well, I mean, water is life, right? So we can't live without water. So that's I don't mean to oversimplify it, but honestly, it's something we cannot live without. And also the landscape is water's plays such an important role on shaping the landscape that in turn influences the way that we live and the way that we um, habitate this planet. And the search for life on other planet is the search for the ability or the capability or the possibility to have water on those planets. So yeah, water is life. Um, Without it, we're in big trouble, you know. Um, so that's one of the, again, not to oversimplify it, but it's very important. And I do think that water does it doesn't play an important role in many of our day-to-day activities, especially those that have a surplus of water, or I shouldn't say a surplus, but too much water is bad also. But those of us that are fortunate enough to have an adequate water supply in terms of quality and quantity, it becomes just an assumption and an expectation for life. But a lot of people on this planet are dealing with either too much water or not enough, or serious issues with water quality and disease spread and things like that. And if you ask those people, I'm sure water issues rise to the top of the list. So it's just kind of this water is an underlying part of our lives that can be underplayed in some circumstances. So I just wanted to showcase that water is important, and that's why I'm dealing with these other issues with water in the biotic environment, not just the hydrological aspects. So so that's important, and that's an important issue. And the second part of that, the answer to that question is that the water cycle is changing rapidly as the environment is changing, as land use and land cover is changing, and the atmospheric is changing. The atmospheric environment is changing quite rapidly with climate change. The water cycle is responding quite rapidly also. So I don't think there's been a time in since humans have been on the planet that the water cycle has been changing so rapidly. So I think it's time to tell everybody, don't forget the water cycle is changing, and we're just beginning to see some of the implications of changes in the water cycle. And I tried to showcase some examples of that in the book also. I think one of the things is we need education, so we need people to understand what the issues are, and that's why we're in the education business and trying to write books that appeal to people that they'll get interested in the subject, and that we need more people to help us out with these problems. We need more enthusiastic scientists to get involved and help us understand the complexity of the problem. And there's many questions out there. So education and outreach, trying to educate people what these are the issues, and this is how significant some of these problems are. And the other aspect, and this is coming from my background as a person who likes to make measurements and trying to measure water, which is quite difficult to measure. It's not an easy measurement to make, especially water vapor, because it's a trace gas. There isn't much of it in the atmosphere, yet it plays such an important role. So education, but understanding that we need better measurements globally of the water balance. There's many parts of the world where we still don't make adequate precipitation measurements. So in order to better manage water resources, we need better measurements of the water balance. And I think that's an important part of the book also, that we need to teach each other and keep pushing on improved measurement technology and make those measurement instruments accessible to people around the world. Like a rain gauge, for example. You could spend hundreds of thousands of dollars on a radar precipitation measurement, or you could distribute really simple to make precipitation rain gauges made out of coffee cans that you could distribute for free to improve the network of precipitation measurements. Same thing with water quality, where we could do a better job at taking measurements, citizen-based science measurements of water quality that could be achieved to get a better understanding of the quality and the quantity of water that we have, and then improve the management of water resources through the better management of them, better measurement of them, sorry. So I think that's an important part also. And the other piece to the puzzle is conservation approaches, where we can always do a better job at conserving water and using it less wastefully. I'll give an example of the North American Great Lakes, where I've been involved in research a lot of my career, and I grew up on the shores of the Great Lakes, so it kind of hits home for me. So the largest freshwater resource we have on Earth, 20% of the world's surface fresh water is stored in the Great Lakes, and millions of people rely upon that water. And so there's been water quantity and water quality issues surrounding the Great Lakes for centuries. And it's always surprising that we still do not know much about the Great Lakes in terms of their water cycle and what controls the water cycle of that very significant body of water. So some of my research has been involved in looking at what controls the variability in lake water levels on the Great Lakes. Why does Lake Superior go up and down by 1 or 2 or 3 meters over the course of a year? And it seems like an easy question to answer, but we still have some uncertainties in understanding what that is. So one of my jobs was to measure evaporation from Lake Superior and the other Great Lakes to understand that component of the water cycle. Because believe it or not, we had very few and very sparse measurements of the evaporation rate from a very important body of water. Because there's no weather stations directly in the Great Lakes, especially in the wintertime when we need to make these measurements. That's an important season, is the wintertime for lake evaporation. So once we were able to measure evaporation from the lakes and understand what are the variables that control it, and then give that information to some of the weather and the forecast modelers, they were able to improve their models of the lake water balance based on our measurements. And that really helped them close the water balance and reduce the uncertainty in understanding the variations in the lake water levels now that they had another piece of the puzzle in place. And so by understanding the water balance and the variation in the lake water levels, that translated directly to better management practices, because now the water balance was more constrained. I know on our campus here, we have like a water week. So it's where a lot of the community comes to campus, and especially the K through 12 school groups, um, K through 6 especially. So they'll come to campus, and the various labs that we have on campus will have demonstrations set up. And at that time of year, it's warm, so everybody's outside. And it's really engaging because it's not just the kids that are getting involved, and that's very important, but also, the teachers and the adults that are involved, and the graduate students that are running these jobs, and the professors. It's a real community building exercise, and it really it's a hands-on how important is water. So those types of activities, community building, engagement, active learning, not just passive. Um, those have worked great for our Water Week. So doing the same kind of things for Earth Day, and I know those events, similar events, do take place at places around the world, but I think those are very, very important, very helpful, and send a strong message. First, explain what is so unique about water as just a substance, and just looking at the physics and the chemistry, and from an overview perspective. Um, if water is so important for life and for shaping the planet, why? So understanding what is it about that molecule that makes it such an important player in our planet. So and again, in doing so, then we can understand why does water, when water freezes and expands, why does it play such an important role in producing soils? And then why are soils and the weathering of the rock material, why does the nutrients that are released, how can they be dissolved in water, be transported through trees and ingested by humans? How can microplastics in the environment migrate into vegetation and into humans, and what are the implications of that? So, so my approach has been to let's understand what that molecule is, and then let's put that molecule into the landscape. And then as life began to evolve and take shape, we can make that connection between that abiotic and the biological environment. So the book kind of builds upon itself, going from chapter to chapter, and the history of water, the origins of water on the planet, how much of it is here, how did it get here, what did it do to shape the landscape, and then how did that influence the life and continue to influence the life upon it. So I think that that theme goes through the whole book. At least I tried to do that. So we can see that water not only shapes us, but shapes the environment around us. It comes into the middle part of the book, and then it gets stronger towards the end of the book. So, and if we think of the three sections, kind of the properties of the molecule, the abiotic environment, the landscape, and then the biological environment. In the middle of the book, it comes into place when we're talking about erosion and the weathering of rocks in terms of the cryosphere, and the distribution of water in its solid, liquid, and gaseous forms, and the melting of the ice caps, and the loss of ice. That's dealt with quite heavily in the middle part of the book, in one chapter in particular. And then also in the middle part of the book, how if we're losing the cryosphere component of the weathering process, how does that have implications for the landscape that we see? And runoff and changes. If we accelerate the hydrologic cycle, how will that affect rivers and erosion, sediment transport? Those begin to take shape in the middle part of the book. And towards the end of the book, where that climatological change and the aspects of climate change in the water cycle get even stronger, because we look at how the water cycle influences life. And there's examples when we look at reptiles and insects, not only how they've adapted to deal with some of the driest environments on the planet in terms of how they deal with the water balance and thermal and water regulation in their bodies and how they've adapted to these dry environments, which has implications for the world getting even drier. So we look at that, and again, with the lens of how are they dealing with these harsh environments on the planet, and if our planet gets even drier, wetter, hotter, what are the implications of that for those life forms and also us, which we get to in the later part of the book. And then we deal with things such as heat stress and heat stroke and the water balance of a person. And the real interesting part there, and again, this part I don't think I see much of in textbooks, and heat waves and heat stress and heat stroke are becoming more and more prevalent every year. Every year is worse than the year before it. So there's thousands of deaths every year due to heat stress and heat stroke, and those numbers are going up. So we look at the thermoregulation and the role of water in thermoregulation of a human, and see how not just the consumption of water, those aspects, but also as the humidity outside is changing and air temperatures are increasing, how does that play a role on the ability for a person to maintain a normal, comfortable body temperature and not suffer from heat stress? So that also gets the final chapter when we look at changes in climate change in terms of humidity and water vapor. Then we see how is water vapor changing in the atmosphere as the system is warming, and a warmer atmosphere can contain more water vapor, and what are the implications of that for thermal comfort for a person. So it begins in the middle and then ramps up and kind of ends at the end of the book. The last chapter kind of ends on this is a serious thing that we need to try to pay attention to. And a lot of people don't realize, how the atmosphere wants water too, right? So the atmosphere has a demand for water, and as it gets warmer, it demands that it has more water. So it's a consumer of water also, and that's the part that can really affect human comfort, and it's deadly. So, and personally, I think that's an exciting part. It's exciting, not, and I don't mean it's a good thing by any means, but it's exciting because I think that's a really fascinating aspect of water research that few are studying and few pay attention to. It's an aspect. It's not just water quality. I mean, that's critical also, but how a living organisms, us and other creatures and vegetation are also adapting and trying to cope with a warmer environment. That's a pretty important topic. I think we're just at the beginning of understanding and trying to get our hands around how to convey this to the public. You're right. I mean, the thing we can do about it is try to not warm up the planet so much, and things like in terms of urban environments and planting trees to increase shade and water vapor, cooling through natural means and building design. There's people working on that, and that's important. White streets, something as simple as painting roads white instead of the black surfaces, that can have a significant impact on temperature and then therefore on the human water balance. But so there's those things. But in terms of when we have tens of thousands of people dying every year from heat stress and heat stroke, one of the issues is how do we measure how the effects of combined temperature and humidity, how do we measure and then calculate what the impacts of that on the human body? And right now there are all kinds of different indices that are used and all different kinds of combinations of measurements that people put together to come up with what we call an effective temperature. So if the temperature is 25 Celsius outside, when you combine the humidity, it could feel to our bodies like it's 35 degrees Celsius. And therefore, it's not just the air temperature, you need to pay attention to the humidity. And then coming up with a way to combine all these variables through proper measurements to come up with an index that means something to people. There's a real challenge there to do that because there's different ones, and different agencies and countries are using different indices, if they're using any at all. So So there's disagreement. And if traveling through Europe, Italy will use one index and then France will use another. And then what happens is any warnings that come out are based on those indices. So like a heat stroke or heat stress warning could be issued depending on the index that they're using, which can get confusing because one country could have a warning in place and another country might not. So when the countries are very close together, it's like, okay, should I be concerned and drink more water or should I not? So just the way this information is disseminated to the public is an area of active research right now. What's the best way to do it? In a way that people will take heed and not have their kids or themselves go out and do some rigorous activity and not be aware that their water consumption should increase dramatically under those conditions, or maybe they should delay that activity until things cool down. So just the public awareness, as scientists doing a better job at getting that information out there in a way that's easily understood and digestible, that's something that we can improve upon. One, I would say, and I see this quite a bit, is don't be afraid of science, don't be afraid of math, and don't be afraid of chemistry. And they can be daunting. And I see this every single day, is that there's an individual, a student that is really interested in the topic, but they get turned off the topic or feel that they can't have a career in this area because there's too much math, there's too much chemistry. Um, those those can be learned, and it's just like trying to learn a different language. It's a steep learning curve, but once you start using it, you will get good at it. So everybody is capable of understanding these topics. And that was, again, back to your earlier question, that was one of the reasons for writing this book, is to speak to those people, and not exclude them from the conversation, because we need all the help we can get. So don't be afraid of the math, and don't be afraid of the chemistry. Don't let that be the barrier. And because everybody's capable of doing it, it just takes a little bit of elbow grease and some work to get used to the language of science. It's just a different language. And don't let anybody tell you that you can't do it, because everybody can. So I think that's really, really important, is that bit of advice. And the other bit of advice I would give is to keep your networks open and keep networking and meet people that are working in the area. And those connections are really important. So meet people, go to conferences, take the classes that are of interest, and ask questions, and be an active learner, and don't be passive. Don't sit there and have the professor speak at you and hopefully rely on osmosis for that information to get into your head. You have to learn actively, get involved in research at your university or college, wherever you are. Volunteer to do something that opens a lot of doors. It doesn't pay the bills, but volunteering can be a great thing. There's all kinds of local water studies going on that you could get involved in. So don't learn passively. Learning takes an effort on the person who's learning. So